Hello everyone, welcome to the problem solving session for week 5. So this week, I hope this pad is visible and legible for everyone. So this week, the major topic of interest were two things. One was similar to the previous week, redundancy, and second was redundancy resolution. Okay, so what we'll do is we'll just uh, briefly go through what does redundancy mean and what does redundancy resolution mean. And while going through these definitions, we will go through some examples that will help us understand what does these terms look like, right? So redundancy, okay, it is a system is said to be redundant when it has more actuations than the number of degree of freedom. Okay, so like a very, very crude definition. Number of actuations is greater than number of DFs. Right. But this definition of redundancy is not a complete one. Okay. Why? Because there can be uh, scenarios where these actuations are all orthogonal to a certain degree of freedom, right? So no matter how many the number of actuations there are, they just cannot affect a certain degree of freedom, right? But but when we talk about planar manipulators, then this very crude definition of ours is actually sufficient to classify a system as a redundant system or a non-redundant system. Okay, so if a system is not a planar manipulator, right, it's either a general 3D manipulator or let's say it's a quadcopter or it's a uh, let's say, yeah, let's take an example of a quadcopter, right? So a quadcopter, as we had discussed earlier also, it is an under actuated system, right? Why? Because it has total 6 degrees of freedom and it has 4 independent actuations, right? But what happens when we add 2 more rotors here, right? Now it does have 6 independent actuations, right? But this is still, right? This is still an under actuated system, right? It is not a redundant system right now. Now, to see why that is the case, we need to understand that all these actuations, right, or these rotors in a multicopter, they only affect the rotational degree of freedom, right? So you can essentially say the rotational degree of freedom in the height and the z degree of freedom, right? So total DF are 6, right? But controllable DFs are only 4, right? What are they? They are the orientation parameters and the z height. Okay, so what that means is that in a quadcopter, we cannot control the x and y directly, right? How do x and y change in a quadcopter is because these quantities are coupled, right? So we control these quantities, and then these quantities in turn cause our x and y to change, right? So again, now now since this was the case for, like, we saw that there are only 4 controllable layers, so that's why if we have four you know actuations, or 4 rotors. Okay, so this exactly matches your number of controllable layers, right? So that is why 4 is the minimum number of independent actuations that you need to stabilize a quadcopter, to stabilize the orientation as well as the height of the quadcopter or any multi-rotor, right? Now, even if you add 6 actuators, right, like we did here in this case, okay, you add 2 more rotors, okay, or you can add any other actuation. You can add, rather than adding rotors here, you could have just added servo motors here. You could have just added, servo motors here at the base of all these rotors. So what the servo motors could have done, they could have tilted the rotor, right? If the plane of a rotor was initially this, then they could tilt the rotor, right? So there are different ways to increase the total number of actuations, but as you can see, there are still only 4 quantities that can be controlled in this way, right? So in this particular case, in the case of a hexacopter, so a hexacopter is actually a redundant system. Okay, so we saw 2 ways till now, right? Not 2 ways, like just one way to identify redundancy, and that was we see what are the number of controllable DOF, and then we see what are the total number of control actions available, right? Independent control actions. And when the total number of independent control actions is greater than the total number of controllable DOFs, we say that our system is redundant. right? Now, how do we get these controllable DOFs, right? So I think that is a discussion for some other class, and sir will discuss it. But if I'll just give a brief idea for a linear system of this type, right? So this B matrix for any system will give you information about which degree of freedom or which X is, you know, modifiable using U, and which X is not modifiable using U, right? And so this, and also you can try getting the rank of the controllability matrix, right? If you know the concept of controllability matrix, you can try to, like, again, for a linear system, you can get the controllability matrix for the, or for non-linear system, you can get controllability measures for that particular system, like the Gramian, or, then you can decompose the system into two parts, one that is controllable and one that is not controllable. And then you take your analysis from there, right? But we just now, there are other methods basically to identify which degree of freedom are controllable and which are not. Okay, so uh, again, till now we just have seen one way of identifying redundancy. The other way of identifying redundancy is using the Jacobi, right? So what do we mean by this particular thing is that, you see, uh, when we define a task, right? Uh, for example, a task can be defined, you know, uh, let's say, we take a very basic example of a 2-hour manipulator, right? So a task can be the position of the end effector, right? So this is a very simple uh, task that we have taken, that the position of the end effector is something that we want to regulate. Okay, and this mapping is actually a straightforward forward kinematics mapping where theta and x are both vectors, right? This x is denoting the x and y coordinates of the end effector, and this vector theta, this denotes the relative angles theta 1 and theta 2, right? This is theta 1 and this is theta 2. Now, when we define a task like this, as you guys have seen in the previous week, we can also define a differential mapping for this, that is given by this equation, right? And this matrix J here is the Jacobian matrix. Okay, now what we will assume is, right? Not assume, like in this particular case, the x, right, it belongs in R2, and theta also, it belongs in R2. Okay, so when we see this mapping, right? When we see a mapping from theta to x, right? It is a one-to-one mapping, right? Because for every, it is not exactly a one-to-one mapping in this particular case, because there are two different set of theta that achieve a single x or a single or the same interfactor coordinates. Okay, but like it can be one to many, right? But it is certainly not what you would call a many to one, right? Or I think I've said it the other way. It is not a one to many. Hi Dalio, so if you plan to stick around, then you can stay. What I'm doing is I'm recording a lecture right now, and I'll upload it later, and you'll get the link as you have been getting till now. So yeah, you're free to stay, but you can leave also, because I'll be just continuing with this recording kind of way that I'm doing for this lecture. Uh, I would like to get some response. Yeah, thanks. So yeah, in this particular case, it's a many to one mapping, right? There are multiple values of theta, right? But exactly two that can achieve same x, right? So why is that the case, right? Why is not it is not a one-to-one mapping, right? It is because the task that we have defined, right? The task that we have defined and the total degrees of freedom of the space are different. Okay, what do I mean by that? Is that a 2D space, right? We know that a 2D space can be defined by any two numbers. That's why these, x and y, they can just, define any point in the 2D plane. But when we talk about rigid bodies, we know that in a 2D space, you have two dimensions for translation, but you also have one dimension for orientation, right? So this is a total of three dimensions, right? And if you consider all these three dimensions, right, in your x, right, let's say we define, let me flip it over. Yeah, let's say we define x1 now as x and y and theta Not theta, we'll call it alpha, where alpha is the angle of the end effector, right? The total orientation. In our particular case, right, this is theta 1, this is theta 2. So alpha would be theta 1 plus theta 2, right? Now, if we were to define this as the task or the mapping, right? So in this case, the mapping from theta to x1 is indeed 1 to 1, right? Because even if you try, when you try to take the other branch to reach the same end effector position, the alpha is different here, right? This angle alpha here is different. So that's why you need to consider the total number of, you know, degrees of freedom you're working with, the total number of components in your task, and the total number of actuations here. Okay. And one way to resolve all this is to get the rank of Jacobi, right? So basically, the rank of your Jacobian should be able to tell you if a system is underactuated or not, right? So in the previous case, from theta to x, you could actually say that the system is underactuated, right? Because you have in total 3 degrees of freedom to control, but in reality you can control only 2. So the third degree of freedom is somehow getting determined by the choice of the branch, right? So again, it depends. So rank of J can be used to determine underactuation. Okay, but let us consider one case when our task was same, the end vector position, but now we have a 3R manipulator, right? So in this case, we are not, you know, it is still a many-to-one mapping, right? But now there are not just two distinct possibilities for uh, the values of theta for a given x and a given y. There are actually infinite possibilities, right? If you try to draw this kind of structure, right? So this is your 3R manipulator, theta 1, theta 2, and theta 3. Okay, so this now you see you can achieve any xy, right, by infinite combinations of these thetas, like right, theta 1, theta 2, and theta 3. And why is that the case? It is because you have three independent degrees of freedom and you are trying to control only two independent degree of freedom, right? In earlier cases, we had not a unique but two distinct solutions. In this particular case, we have infinite solutions. right? If we say we talk about the mapping from you know, from theta to x, in this particular case, there are infinite theta, right? For any x in the workspace, right? And why is this the case? We all know that when your number of variables, you know, is more than the given number of equations, right? You can treat this as the given number of equations because x is 2 and the number of variables is 3, right? So of course you have an underdetermined system, so the range of possible solutions is infinite, right? And in this particular case, if you try to write the Jacobian, right? So now Jacobian, since the dimensions have to be consistent with those x and theta, okay, this will be a 2 cross 3 matrix, right? So you can also, look at it this way that there are these vectors in the column that span the column space of the Jacobian, you know, that you are then mixing, or then you're taking their linear combination with this vector theta dot to get x dot, right? Now since x is a two-dimensional space, right? So all these ji's, they're 2D vectors, right? They belong to R2. And our x also belongs to R2, right? So we can write x dot in this particular case. Ji theta I, right? We can write x dot like this is the summation convention that we're using right now. You can write it as j1 theta 1 dot plus j2 theta 2 dot plus j3 theta 3 dot, right? Now since you have only two equations but three variables to find out, of course there can be infinite ways in which you can get these values. Now there are infinite ways that you can get these values, but if you impose some rules on these values or on this system, then you can try to get an optimal value in any sense that you want, right? One of that sense is the least square sense, right? What is the least square sense? That you want to get x, right? So you choose a particular value or you get a particular, so you get theta that can achieve x hat, and then you make sure that while choosing theta hat, we make sure that the least squared error between x and x hat is minimum, right? Good enough. This particular thing, it works well in many cases, right? You're not achieving exactly what you wanted, but you are trying to get as close to it as possible in an optimal sense, right? In a least square sense. So if we say how we are going to do this, so if this is our equation, right? This is very similar to ax equal to b kind of equation, right? And we want to find x. Okay, in this particular case, it is theta dot. So how we go about doing this, right? Because we cannot invert j directly, remember? Why we cannot do that? Because j is a non-square matrix, right? Or j is a 2 cross 3 matrix, right? So unless it's a square matrix and it has full rank, we cannot invert it. So what do we do then, right? We make this a square matrix, right? So there are two ways to do this. Either we do this by intuition and we say, yeah, we make it a square matrix, or what we do is we use this equation, right? So what we say, error is x minus x hat, right? And for this case, it is x dot minus j theta dot, and we are trying to minimize e square, right? Or in if we are writing in terms of vector, we are minimizing e transpose e, right? Okay, minimizing with respect to x. X dot minus j theta dot transpose x dot minus j theta dot. Okay, we'll go forward with this. Okay, so what we are trying to do is we are trying to get theta dots for a particular x dot, for a particular chosen x dot. Okay, now we'll just open this up. X dot transpose minus. Okay, one thing we wanted to find theta dots that minimize this. So yeah, we get this, we get this, Okay, so we get this equation and we want to get theta dots that minimize this. Okay, so right. So the best way to go forward, or like what we actually know, that for unconstrained optimization, for a continuous function, and if you have an unconstrained optimization problem, then the function achieves a minima where its partial derivative with respect to the variables that you're working, or whatever variables you're looking for, is zero, right? So basically we want to take this, let's say we call it L. So del L over del theta dot in this particular case is zero, right? So any theta dot that satisfy that are, close to our, is our solution in a least squared sense, right? So if we now differentiate this, we get minus J transpose X dot minus J transpose X dot again, and then plus J transpose J theta dot, right? And this we want to be zero. Now here we can say this will be twice, right? Now here we can see that this is a square matrix, right? So we can try to take an inverse of this, right? So theta dot in this case is, yeah, J transpose J, J trans inverse J transpose X dot, where this is what we call the pseudo inverse, right? Or the Moore Penrose inverse, pseudo inverse or Moore Penrose inverse, right? So to get a solution of the differential relation that we had, right? Right. So to get theta dot in a redundant case, right? When you have infinite possibilities of theta to get any x dot, this is how you choose a unique theta dot, right? You use a pseudo inverse, right? I think this is also a solution to one of the problems this week. So I think that works out, right? And now, if we delve into it a bit more, a bit deeper, then we can say that when we are taking pseudo inverse, we are partitioning the total space into two different spaces, right? One defined by the column space of pseudo inverse, and one defined by the null space of J, right? So what do we mean by that? We will continue from here, right? But what we'll do is we will change the notation where we had theta dot in place of x and x dot in place of p. Okay, so that we have a usual convention here. Okay, A transpose B. So now if we actually try to write, you know, the B that we got, right? So again, we said that if we use this, if we use x hat, this optimal value that we have calculated, we won't get exactly B, right? But what will happen is this error between B and B hat will be minimized. Okay, so it can also be seen in a way like this, that if your target space is this plane, right? But you have your vector B here, right? Then this perpendicular error, right? Because this is your target plane, so all the solutions must lie within this plane. So this perpendicular error is what basically we are trying to minimize. These two are slightly different. Why? Because here we are trying to project the your vector B onto a low dimensional space. But in our original example, what we're trying to do is we are trying to, extrapolate the value from 2D to 3D, right? But we want to do this extrapolation. So in that case also, your vector x dot lies in the plane. Now you want to get a 3D vector, okay, that has a minimum error, right? Simple as that. So slightly different, the two problems that we talked about, but not so much different, right? If we just plug in the value of x dot that we have here, okay, so this is the value of b hat basically, right? Now you see this whole vector here, right? Hmm. This complete vector here is the complete matrix here, right? This somehow can be seen as the projection operation, right? That this matrix projects B to B hat, right? So this projection matrix projects B here from this space to the other space that we want. And in the second case also, when you are projecting from 3D to 2D, the projection, works in a similar manner. Now, since this projection is either into or from this plane, right? The space perpendicular to, you know, whatever your uh, space in this particular plane, it is still, this is what we are choosing basically when we are going from 3D to 2D and from 2D to 3D, right? So in this particular case, what we got was we got a minimum norm solution, right? We got theta dot that has the minimum magnitude, right? While achieving all the different things, right? Because J here has a rank of 2, right? So it is a bit tricky to get theta this way. But yeah, this is how we can actually try to get the solutions to this. Okay, and now if we try to take the difference between B and B hat, right, we get, identity matrix, because, if we replace this by PB, right, you can also write B as IB, I minus PB, right? So this P is what we call the projection matrix, and this space defined by identity minus P is called the null space. And this null space is what is used for redundancy resolution. And this is another term that we were going to discuss today, right? Redundancy resolution, that if you have multiple tasks, right? If you have multiple tasks, then what you can do is you can do one task in the space defined by the projection matrix, and then you can do another task in the space defined by the null space matrix, right? So if we try to, you know, write this, write the total solution x, right? So it will be x hat plus some, you know, value of some value in the null space. Okay, and this we saw was the pseudo inverse, right? Now the idea is, when you know you have chosen x hat for a particular task. In this case, the task was B, right? Okay, and you have a redundant system. You still have some, you can say, control effort left, right? That you can use to achieve some other tasks, but in the null space of the present task, right? So what does null space mean? It means that whatever, you know, control action, if we, let's say if we replace this with theta dot now, whatever theta dot we choose now will not affect, right, in this null space, whatever we choose, it will not affect our result in the initial task space, right? Because these two task spaces are orthogonal. This is A dagger B. Okay, so this is what we use for, redundant manipulators or redundancy resolution, right? In general. Now there are two kind of pseudo inverses. One is left pseudo inverse, one is right pseudo inverse. That depends basically on, where your matrix A, is it a, you know yeah, your matrix A, is it a, long matrix, or it is a wide matrix, right? So like if you say that it belongs to m cross n, right? So either when m is greater than n and when n is greater than n. Okay, so both these cases have different expressions for the pseudo inverse, and what we have used here is called the left pseudo inverse of A, right? This particular expression, this is called the left pseudo inverse of A, and it is usually taken for cases when you have a long matrix, right? when you have more observations for and then you want to get a particular x, right? And this null space is also, you know, this this null space that we got here, right? This is also called the kernel operator, right? This is just the linear algebra way of calling a null space projector matrix, right? We call it a kernel matrix or a kernel operator. It projects any given vector into the null space of your A matrix, right? So now, okay, if we, let's say, take a question that if we have an n-link, you know, serial manipulator, right? If joint velocities in this particular case are contained in a unit sphere, right? It means that yeah, that the total norm of all these um, you know velocities is 1. Then what do we have? Then the end effector velocities, they make, what is the shape that they make up? Okay, so how do we, hmm, yeah, okay. So if you try to think about it, if see, if you have x dot equal to j theta dot, right? Now you want to find norm of x dot, right? How do you find norm of x dot? You get by, right, square root of this. For now, what we can do is we can take square of this. Okay, so we just get x dot. Okay, now if we like put this expression here for x dot, we get this, right? So this clearly now is a mapping from, you know, if norm of theta dot is 1, right? The norm of x here is just some scaled version of the norm of theta, right? I mean, you can also call this the weighted norm of theta dot, right? If I just call this a matrix W, this J transpose J, this becomes like this. Okay. Now what it means is that if initially theta was in a sphere, right? Now, right, and there was this theta 1, there was this theta 2. Now, according to this W, based on this W, this will get, elongated in some direction, right? In some direction, it will get elongated, and in some directions, it will shrink, right? Based on the eigenvalues of your W matrix, or based on J, right? Based on the eigenvalues of J, because eigenvalues of J and J transpose J will be the same. So this will be the final mapping, right? This weighted norm of the given norm, right? Given uh, norm of theta dot. So what is this shape? This is an ellipsoid. Now, if this is an n-link manipulator, right, then this will be a n-dimensional ellipsoid, right? So now don't be confused, right? This x dot, right, in this particular case is still 2D, right? But the velocity, it will, you know, if the joint velocities are contained in a unit sphere, right, then the end effector velocities, the magnitude of those velocities will be contained within a n-dimensional ellipsoid, right? And where did this ellipsoid come from? We saw here, right? Because we are talking about the norm, that what is the shape that the velocity vector can lie. Okay, so what is the norm? What is the maximum norm, right? And we are getting a shape for that. So yeah, like just keep that in mind, right? And let's say we have, like, I think we have already discussed this thing that what we have discussed is that, right, for control of manipulator, right, we can use task prioritization, right? And how do we do that? If we have, let's say, 3 tasks, y1 j1x, y2 is j2x, and y3 is, right, j3x. So how do we get x? Is that we take pseudo inverse of y1, right? Now this is based on priority. Y1 has more priority than y2 and y2 has more priority than y3, right? This is the assumption that we're going with right now. That is why we start with y1, right? Now, if J1 is a non-square matrix, then there will exist a null space for that, right? Let us call, this as the P1, as a projector matrix for J1. Now, in this null space, let's say we just write x naught, right? And now we know this x naught can be used to achieve other priority. So this x naught here will now become J2 dagger y2 plus I minus p2. Let's call this x1, right? Now this is further down the line after two null space projections. If there is some dimension that we can still use to achieve a third priority, then we do that. J3 dagger y3 plus I minus p3 some x2, right? Now if you just put these here, then you will get your final expression, right? For uh, the task prioritization based redundancy resolution, right? Because now you have the final x that takes into account all the three tasks, right? It will try to achieve all the three tasks, but in priority, right? And the way that this solution has been set up is that to achieve task 2, it cannot compromise on task 1, right? Because it is achieving tasks 2 in the null space of task 1, right? And how do you get this P1? Usually it is this, right? For the for the left pseudo inverse. And if you're taking the right pseudo inverse, right, it means if your matrix is wide instead of long, then this is the projection matrix, right? Just, this is why I'm using P here instead of, just writing JJ dagger or J dagger, because your projection matrix can change depending on the structure of the problem, right? So yeah, like this is also one of the concepts that we use in hierarchical control. So yeah, pretty easy. So I think I'll leave it for now. This is more than enough for you guys to solve the questions this week on your own. And like almost all of them, I think, are just objective questions, and they don't even involve some calculation, so you'll be able to do that. So I think I'll stop the recording now.